Hi, this is Marco from the University of Milan, and I'm presenting efficient and near optimal algorithms for sampling connected subgraphs. We study the following k-graphlet sampling problem. You are given a graph G and you are asked to return a uniform random connected subgraph on k vertices of G, also called a graphlet. This is a problem that pops out in social network analysis, bioinformatics, and other fields. We use the graph access model that in constant time allows you to perform a degree query, a neighbor query, or an edge query. Let me summarize the state of the art. For uniform graphlet sampling, basically nothing is known, meaning that all the algorithms known require a running time that is linear in the size of the graph for every sample that you take. For epsilon uniform graphlet sampling, things are a little bit better. Epsilon uniform graphlet sampling is the relaxation of uniform graphlet sampling, where you are only asked to return a graphlet from any distribution that is epsilon close in total variation distance to the uniform distribution. There are basically two techniques here. The first one is color coding, which is a two-phase technique. It has a preprocessing step that runs over all the graph 2 to the order of k times. After that, you can sample epsilon uniform graphlets from G in time k to the order of k per sample in expectation. The second technique is a one-shot or a direct sampling technique where you have no preprocessing. It's a technique based on random walks. The problem of this technique is that the running time depends on the mixing time of the walk that it performs over the graph G. And that mixing time is not so easy to analyze. The best bounds known so far can be as bad as the number of vertices of G to the power of 2k-1. So that's very large. The question that we ask in this work is, of course, if we can do better. We give several results that show that, yes, we can do better. The first result is the first efficient algorithm for uniform graphlet sampling. It is a two-phase algorithm with a preprocessing time that is linear in the size of the graph and a sampling time that is logarithmic in the maximum degree of the graph, delta. And this algorithm is based on a surprisingly simple trick that is basically sorting the graph G in the preprocessing, so to make efficient rejection sampling at sampling time. For epsilon uniform graphlet sampling, we also give results. I compared to the color coding algorithm that I said above here. And in this work, we show that the preprocessing time can be brought from being linear in the size of the graph to be in the order of n log n. So this means that if the graph G has enough edges, say it has average degree polynomial in n, we have a sublinear time algorithm for sampling epsilon uniform graphlets. And the sampling time remains constant in expectation as it was for the color coding technique. Our second contribution for the epsilon uniform graphlet sampling is to provide tight bounds for the running time of the random walk approach. We show that the mixing time of the random walks can be expressed as follows. It is the mixing time of the graph G times the ratio between the largest and the smallest degree of G, big delta over small delta, to the power of k-1. Which means that basically the random walk performed by this technique, which is random walk not on G, but on subsets of G, can be thought of as the original random walk on G slowed down by a factor equal to the ratio between the max and mean degree of G to the power of k-1. In the present talk, I will focus on the first two results, so the uniform algorithm and the epsilon uniform algorithm. Both of them are two phases algorithms. They stem from the same technique, which is the one that yields the uniform sampling algorithm. That one, the uniform algorithm, is the simpler one to explain, so we'll start from there. And the epsilon uniform sampling algorithm is, let's say, a refinement, but it's actually much more complicated than the uniform sampling algorithm. So I will try to describe the essential ingredients in it. Let me start from the uniform graphlet sampling algorithm. I recall that I claim that, that we can achieve a preprocessing time of basically n plus m, and a sampling time that is logarithmic in the maximum degree of G. Let me start with a very generic approach, which shows the limitations of rejection sampling and how we overcome that. The basic idea is to perform the following cycle until we accept some graphlet. We choose a vertex V of G at random according to some distribution. Then we explore the neighbors of V, and in this way we draw a random K graphlet from the graph. Let's say, for example, this happens. Then we compute the probability that I denote by P of G, that the first two steps return exactly the graphlet that I have seen. And at this point, I can perform rejection sampling. I will accept the graphlet with the probability Px that is inversely proportional to the probability that I computed. I must make sure that this probability is well defined so that it lies in 0, 1. And so the constant C at the numerator must be sufficiently small. Now, these techniques ensures by construction that you obtain, you return graphlets that are coming from the uniform distribution, but the problem is that you could have a probability of acceptance that is very small, in the order of 1 over n to the k minus 1. That means that you may need order of n to the k minus 1 iterations before accepting one graphlet. That is too much. The idea for the uniform graphlet sampling algorithm is that we can make rejection sampling efficient by a very simple trick. We basically sort the graph G. In particular, we sort G by repeatedly deleting a maximum degree vertex from it. And after doing this, we sort both the vertices of G and also the adjacency lists of G. This will be important. Now, let GV be the subgraph induced by vertex V and all the vertices after V in the order. And let dV given GV denote the degree of V in the subgraph GV. Like in this picture, for example. Here we have the subgraph G3 induced by nodes by vertex 3 and all vertices after 3 in the order. So the graph here is ordered left to right according to this ordering. I will call this degree dominating order. And for the reason that by construction, dVGV, the degree of V in GV, is the largest degree in the subgraph GV. Now define the bucket B of V as the set of all K graphlets of the subgraph GV that contain node V. So in this case, for example, is the set of all K graphlets that contain vertex 3 and contains only vertices in G3. So every vertex in G will have its own bucket, and you can observe that the set of all K graphlets of G is partitioned into these buckets. We are basically assigning to every graphlet a representant node, which is the smallest vertices, the smallest vertex in that graphlet. In this case, vertex 3. Now observe that any graphlet in the bucket of vertex V can be constructed as follows. We start from vertex V itself, in this case, vertex 3, and then we do a search where we progressively include nodes through a spanning tree of the graphlet. And now the crucial observation is that node, the vertex V, in this case 3, has degree dV given GV. And every other node has at most that degree in GV. So by this observation, we can make 3 useful claims. The first one is that the number of graphlets in bucket BV is roughly the degree of V in GV to the power of k minus 1. This holds by simple counting arguments on spanning trees, using the fact that just said of the degree domination. The only approximation that we have is that this holds up to k to the order of k factors. The second claim that we can make is that we can sample graphlets from the bucket of V with a probability that is roughly uniform, again, up to k to the order of k factors. How do we do that? Well, we start with vertex V itself. We look at the cut between V and the rest of the subgraph GV, and we choose a random uniform edge in this cut, and we add the corresponding endpoint, as I showed in the animation before. And we repeat this until we obtain k distinct vertices. By the same argument as for the size of the bucket above, you can see that this procedure yields a graphlet that is approximately uniform in the bucket of V. Okay, these 2 claims follow by the fact that the vertices of G are sorted by the degree dominating order. Now, if the adjacency list of every vertex in G is sorted by the degree dominating order as well, then we can also claim that we can sample graphlets efficiently. So this sampling takes time proportional to the logarithm of the maximum degree. Why is that? Well, the only expensive operation that we make during this sampling routine is computing the cut between the vertices that we have already selected and the rest of the GV. And to compute this cut efficiently, we need just to locate the edges between the vertex and GV, which can be done by binary search on the adjacency list of that vertex by searching for the position of V and considering all the elements after that vertex after the position of V. So this shows that we can sample as described above in time proportional to the logarithm of delta. And also we can, given any graphlet G in the bucket of V, we can compute the probability that this sampling routine produces exactly G. And we can do this essentially by emulating the sampling routine and summing up probabilities. The only thing is that we have to account for the several possible orderings of the vertices of the graphlet in which the graphlet can be actually built by the sampling routine. So this adds a k factorial factor that accounts for, that is responsible for the k to the order of k factor there. Okay, so with all these ingredients in place, we can have our uniform graphlet sampling algorithm, which has, as said, 2 parts. The preprocessing is the sorting of G, which can be done in linear time by a simple bucketing technique. There is only a small additional cost, k squared log k, due to the fact that we have to check actually if every bucket is empty or not. And then we will assign to every bucket an estimate of its cardinality, which, remember, is the degree of V in GV to the power of k minus 1. This is our bucket size estimate BV. With this, we go to the sampling phase, where at each invocation, we draw a vertex V with probability proportional to its estimate bucket size. Then we sample a graphlet from the bucket BV using the routine run grow, which is the routine with a random cut edge selection that I described before. Then we compute the probability that the graphlet will be returned by this procedure. And finally, we do the rejection step. If you replace the probabilities in the probability of acceptance Px, you will see that this probability is well defined and is bounded from below by k to the minus order of k, which means that after k to the order of k trials in expectation, we will accept some graphlet. And by multiplying the running time bounds, you will obtain the expected running time bounds for the sampling phase. So this concludes the overview of the uniform graphlet sampling algorithm, UGS. And let's move to the epsilon uniform sampling algorithm. As a reminder, here I claim that we can achieve a preprocessing time which is n log n times a polynomial in k then 1 over epsilon, and a sampling time that is polynomial in 1 over epsilon times k to the order of k factors per sample and in expectation. Okay, so the big obstacle here is to achieve the n log n preprocessing time. To this end, recall that to achieve uniform sampling, we had two crucial ingredients. The first one was the degree dominating order over the vertices of G. That is an ordering that ensures that the degree of vertex V in GV is the maximum degree in subgraph GV. And the second crucial ingredient for efficiency is that the adjacency lists of the graph G were sorted by the degree dominating order as well. Both these ingredients require preprocessing time n plus m. But here now we aim at a preprocessing time of n log n. So the strategy for epsilon uniform sampling is that we will sort the vertices of G only and not the edges of G by a suitable approximation of the degree dominating order. And then using this suitable approximation, we will kind of approximate the sampling phase of the uniform algorithm, which means that we try to mimic that phase as close as possible in order to make the same decision as the uniform algorithm in its sampling phase. Now, this is easy to say, but it is less easy to do because what you will try first doesn't work. For example, you might think, let's just sketch the graph G by taking, for example, n log n random edges from G. And then let's compute a degree dominating order over this subsample of G. Well, that doesn't work. Even more sophisticated attempts actually fail. The same holds when you try to mimic the sampling phase of G. For instance, you may say, okay, let's just try to compute the cuts between the current subset of nodes selected and the rest of GV. Let's compute the cuts up to a good multiplicative approximation. Well, that does not work. Since you do not have the sorted adjacency lists, there might be only one edge in that cut, but that edge is buried in the whole adjacency list of the vertices. So you might need to explore the entire adjacency list of a vertex to find the only edge that is in the cut between that vertex and the rest of the subgraph GV. Okay, so how do we do? Well, first we introduce a suitable approximation, a suitable notion of approximation of a degree dominating order, which I call an alpha beta degree dominating order. This is actually a pair formed by an ordering over the vertices of G and a vector of bucket size estimates. These must satisfy four properties. First, if we look only at the vertices of G whose bucket size estimates are non-negative, so these are the buckets who are believed to be non-empty, well, those buckets hold a fraction at least 1 minus beta of all the graphlets of G. Second, if I look at any bucket that I believe to be non-empty, the corresponding bucket size estimate is actually good. Third, if I look at any bucket that is believed to be non-empty, the corresponding vertex in G, according to the ordering, has a degree which is approximately maximum in the subgraph GV. And fourth, there's a technical property that is here for completeness, but I won't discuss it. Okay, so now we will use this order and only bear in mind that we will use alpha and beta both polynomial in epsilon. In fact, I will use beta equal to epsilon over 2, which means that we will focus on the buckets which we believe to be non-empty, so for which BV is greater than 0, and then we will be throwing away only a fraction epsilon over 2 of all the graphlets of G. Okay, now the first lemma that I put forward is that we can compute an alpha beta degree dominating order efficiently. Okay, don't get scared by these quantities. They are the ones that I plug in the final result. But the message here is that this time is basically the preprocessing time of the epsilon uniform sampling algorithm. Only replace beta with epsilon over 2. And the proof of this fact is non-trivial. I just give a short proof sketch with the famous technique of proof by intimidation below here. But the point is that we can compute an alpha beta degree dominating order efficiently in time polynomial in 1 over alpha and 1 over beta times n log n. The second ingredient is that now I take this alpha beta degree dominating order. And now if you give me any vertex such that its bucket is believed to be non-empty, it turns out that its bucket is actually non-empty. And in this time, k to the order of k times polynomial in 1 over alpha, 1 over beta, which in our case is polynomial in 1 over epsilon, we can basically emulate the sampling phase of the uniform algorithm. We can draw a graphlet G from a distribution Q V over the bucket of V that is very close to the distribution PV of the sampling phase of the uniform algorithm. And also we can compute an estimate of the probability that the sampling phase of the uniform algorithm will draw that graphlet. And by using these two approximations, we can show that under an optimal coupling, we are taking the same decisions as the sampling phase of the uniform algorithm with high probability, where by high, I mean 1 minus a polynomial in alpha and beta, which in our case is polynomial in epsilon. In particular, I can make, okay, yeah, again, the proof is non-trivial. You have to estimate the cuts between the graphlet and the rest of GV, as I said before, and you have to apply a careful coupling arguments. And then the point is that we can make this probability of the two sampling phases of the uniform and this algorithm to agree large enough, 1 minus epsilon cube. So with this probability, the two algorithms choose the same graphlet from the bucket of V, and they also agree on the fact of accepting it. This holds with probability 1 minus epsilon cube. And since I can show that the probability of acceptance is at least epsilon squared, by conditioning, I will have that after acceptance, we are epsilon close to the output distribution of the uniform algorithm. And that proves that our algorithm is epsilon uniform. Okay, the epsilon uniform graphlet sampling algorithm is this. It looks like the uniform graphlet sampling algorithm, only with the routines replaced by their, say, approximate counterparts. The proof of this whole epsilon uniform graphlet sampling algorithm is quite long. It actually, well, half of the paper, something like that. But here I squeezed it into just a couple of slides. To conclude, we have given the first efficient uniform sampling algorithm with a linear time preprocessing and a logarithmic time sampling, and the first epsilon uniform sampling algorithm with an n log n preprocessing and a constant time sampling. The open questions that I leave is whether a linear time preprocessing is really necessary for uniform sampling. And the second is if we can get epsilon uniform sampling with a preprocessing that is linear only in the number of vertices of G. Thank you. Bye.